Oh, I gotta do some mistake proofing. Um, again, um, looks like the standard deviation's gone from 4 pounds, about 4 pounds, on average away from the mean to 2 pounds, I believe. Yeah, 2.2 pounds. So the game is with all of our processes is to continue to narrow that bell-shaped curve. And I've kind of laid out, where the bell-shaped curve would be right now compared to when I started out, back in 2006, um, somewhere around 199 pounds or whatever. So everybody did a great job on that. I think we're going to be using that the data analysis pack as we go through this, especially as we get into correlation and again, I think Brent joined us, and I don't know if Lexi heard me too. Today is about planting the foundation with a bunch of concepts that we're going to stay with for a couple of weeks, and they're kind of like, I don't know, they're not easy to chew on when you first see them, and a little bit abstract, but I think you're going to find as we get into hypothesis testing and making data not only talk to us but scream at us. Yeah, this is where we're headed now with this analyze phase. Before I get into I wanted to kind of take a step back and go back to SciPoc for a second because I got Lexi sent me her homework on SciPoc, and I've never had anyone go to these links. This is a serious SciPoc chart, and here's why I love it. And you can chime in anytime you want, Lexi Seeley. The reason I love this is because once this is done, right, and everybody gains agreement on what this process is, and this process is about how do we a robotic end of arm tooling application. That's what she does. You want to chime in, Lexi? You probably explain it better than I do. Identifying applications for it, and then what's the process for? Does it make sense to do one? How do we get it going? It involves, if you look at the suppliers, everybody from production, project manager, mold designers, all these different silos, if you will, maybe. Not in some companies, not so much PTA. But here's why I love it the most is because it's so easy. Once I do this, especially if I have collaboration, everybody agrees to this SciPoc. Now it becomes real easy to do a sim. I didn't do the swim lane. If I had more time, I'd do it, Lexi, for you. But again, the swim lanes would be all these people, all these suppliers. And again, from a lean standpoint, what I'm looking for is the handoffs. And it just and I want to try to eliminate as many of those handoffs as I can to make this a lean process. And again, if we want to do a value stream map, then we would put time to this. We put how long does it take on average to go from swim lane to swim lane? What are our handoffs? And can we collaborate together and figure out ways to eliminate the handoffs? Right. The other thing, I know this is like bonus, so no extra charge for this. But this is the book that we've been reading for our trip to Illinois, Bottleneck Rules, and largely to get into the lean process like this one. And it teaches us how to identify a bottleneck and a whole bunch of things that we can do to improve bottlenecks. But well done, Lexi. Thank you. That was a lot of work. So, all right. So let's jump. Any questions, thoughts? Well done, as usual, guys. Today we're gonna now this is something called inferential statistics, and this is kind of what we're going to get into initially when we get into the beginnings of the analyze phase. It's three sessions. There's no homework today, so maybe you could just digest some of this, the video or whatever. But the idea behind inferential statistics is based on a sample, are there some predictions that I can make? Are there some inferences I can make? Because it's not practical to collect a whole population, right? We have to have a sampling strategy in order to understand our process better. So I think I like this right now because the same steps that we're going to take right today, what I'm going to take you through right now, are things that we're going to be doing when we get into the 10 or 12 or 15 different types of hypothesis tests over the next couple of weeks. And I feel like I could use my weight to do this, but I feel like I'd switch it up a little bit, and we'll talk about the weather a little bit. So let me start with an objective, right? Let's start with that. So the objective is here, the average temperature in Connecticut since 1950 in July is 87.5 degrees Fahrenheit. I made that up. I don't know. You can check Google if you want, but somewhere around there, right? So I said 87.5 with a standard deviation of 3.5 degrees. So the average deviation away from that 87.5 is going to be 3.5 degrees. Last July 15th was 94 degrees Fahrenheit. And the question we get used to asking ourselves is, was that day's temperature statistically significantly different for the average than the average for the month of July? Okay, so that's how we're looking at data, and that's how we're interpreting sample. Is it statistically significantly different? All right. And the way we look at it is there's a bunch of steps that we're going to take. And they're going to be the same steps that we're going to over and over. You guys are going to get tired of me going through these steps with you. One, decide if it's going to be evaluated. Oh, first of all, we're going to look at a confidence level. All right. How confident? It's usually 90, 95, or 98% confident level. Okay. And generally the one we use most is 95% confidence level. All right. And basically those are the goalposts. In other words, when we look at our data, and we have to set that ahead of time. When we do this a little bit of analysis to find out if that day's temperature was statistically significantly different, I want to know with 95% confidence that yes or no, it's statistically different. Okay. I have to pick that out ahead of time, what my confidence level is. Because again, as my confidence level gets higher, then I can become more stringent with when I do my test statistic, which you'll see. So, all right. So the first step, define the objective. What are we trying to find out? What are we trying to learn? It could be December 15th, Bill's weight was statistically significantly different than any other weight. Because then again, as you're measuring your processes, you might see something that looks like an outlier. Like 94 might be an outlier based on, maybe it is, maybe it isn't. We don't know yet. We're going to do the test. Because if it's an outlier, then we're going to dismiss it, let it go. But if it happens as a pattern, becomes part of the process, then we want to take an even closer look at it. So one, define the objective and confidence level. Decide if it will be evaluated by a one-tail or a two-tail test. And all that means is if I had asked you, was that day's temperature statistically significantly hotter than the average? That would be a one-tail test because I'm just asking if it's hotter or cooler. The fact, all I'm asking you is it different? So anytime in a problem statement, because we're going to see a bunch of these problems, when we see different and not hotter or colder, faster, slower, whatever, thinner, thicker, whatever you want to measure, it's going to be, this indicates that it's a two-tailed test. And all that means is when you look at the bell-shaped curve, that is one sloppy curve that I drew with my mouse. But what we're looking at is both ends, right? We're looking at the right edge of the curve and the left edge of the curve. All right, does that make sense? It's a one or a two-tail test. The next step is, and this is again, it's going to be common through all the testing we're going to do. We formulate a null and an alternate hypothesis. In my null hypothesis, the way I think about it is I'm innocent until proven guilty. And what that means is temperature on July 15th was not statistically significantly different than the average for the month of July. So I always start out with the null. The null means no, it's not significantly different. The alternative hypothesis is yes, July 15th was statistically significantly different than the average for the month. The only goal of hypothesis testing, and in this case, inferential statistics, is to disprove the null hypothesis. It's almost like you're on trial, right? And the only thing that it's up to the, prosecution to come up with enough evidence to prosecute. But you're presumed innocent. Well, it's the same thing here. The null hypothesis is that there's no difference statistically. The alternative hypothesis is there is a difference. All right. And then what we're going to do is select the test distribution. I'm going to show you a bunch of different test distributions today. This is obviously a normal distribution because we're looking at data for every day in July since 1950. So we have almost like my weight data, right? Like a lot of data. So most likely it's going to be a bell-shaped curve. It's going to be normal, right? You're going to have a mean, and you're going to have on each side of the mean, you're going to be fairly symmetrical. All right. So I'm going to use, in this case, I'm going to select a normal distribution, which we did with the weight. Remember this one? The Z distribution right here. There's a little formula that we have to put in order to get those numbers so we can plot. So same thing, we're going to select the test distribution and the critical value of the test statistic. And then I'm going to calculate a test statistic from the sample. And here's the formula right here for it. Hopefully I can. So Z is equal to X, which is going to be the 94 degrees that it was July 15th, minus the average, mu, divided by the standard deviation. And what I get there is a Z-score equal to 1.857. Doesn't mean much right now, right this instance, but it's going to in a second, 1.857. And then after I calculate the test statistic, all I'm going to do is based on what test distribution I pick, there's a table for every one of them. And all you got to do is Google them. Google T-table, chi-square table, whatever the distribution is. And I'm going to basically go find out at a 95% confidence level what my goalposts are. All right. So the way this goalposts work, and of course I throw football and everything, is I'm both sides of my bell-shaped curve. You can see the left and the right. There's a goalpost. Now I need to find out where that goalpost is. If my data lands outside the goalpost, like a field goal, it's off to the sides, then I'm going to reject the null hypothesis. And as a matter of fact, I labeled it RR, rejection region. So to find my test statistic at 95%, I'm going to go down to the bottom of my Z table, and I'm going to go across, and I'm going to find 1.96 because that's my 95%. That's why if I had picked a confidence level of 90, then my goalpost would have been 1.645. But because I wanted a confidence level, a surety of 95%, then my test statistic, my confidence, my critical value is going to be 1.96. So I put that 1.96 on my graph, positive and on the negative side. And then I take my test statistic, which was 1.857. And where do you think that would land on this graph? Dan?
It would be more, it would be to the right, right before, because it's 1.8.
Right before my rejection region, right?
Yeah, before the 1.9.
So it probably lands somewhere in this area, right? I don't know if you can see my mouse or not. So what does that tell me about my null hypothesis? Can I reject my null hypothesis, or do I have to accept it?
You should accept the
Bingo.
null.
Good job. Exactly. So that's all we're going to be doing. You know what I mean? It's like, so it's going to be different data sets, different distributions, different formulas, different tables. But when it comes down to it, the only thing we know that 94 degrees is not statistically significantly different than the average for the month of July. All right. So that's your first crack at hypothesis testing and inferential statistics. And again, we call it inferential statistics because we're trying to make inferences from data, from samples. Oh, cool. Everybody kind of get it. Define the objective, confidence level. Is it a 1 or 2 tailed test? Formulate the null and alternative hypothesis. Select the test. The hardest part is picking the right test distribution and critical value. You know, the formula for the test statistic. But that's what we're gonna work on a little bit with different data sets. We're gonna look at a whole bunch of different things. Sound good? Simple as that. So let's get into the PowerPoint. It's gonna make it a lot easier, I think, as we get in. Oh, dumb Bill. Hold on. I gotta open it. Didn't do that ahead of time. Lack of preparation. Analyze phase. Right. Oh. All right, people. You see it? It's pretty good. And I'm gonna open up my notes. All right, you guys see everything okay?
Yep.
Yeah. All right, so here we are. Again, spent 3 weeks in define, 3 weeks in measure, 3 weeks in analyze. I think it's 3 weeks in improve and 2 weeks in control, I think. So we're starting our analyze phase. Define the problem. What do we need to improve? How do we measure it? And now analyze the process and define those vital few factors. What are they? That if we change them, then we can improve our process. So it's about finding the vital few, the 1 to 3 causes of the problem being addressed. It's always 1 to 3. It's not 100. If it's 100, then we're not doing it right, or our process is way out of control. Right? It starts with the team input regarding causes, and we use statistical methods to isolate the top 1 to 3 causes. And here's what we'll be covering. I think I skipped a slide. Yeah, I did. Statistical notation. We're going to see a lot of this, as you saw already in the formulas, as we go through them. You'll see this table throughout the analyze phase, just to kind of a reminder of what's being asked for. And we'll start with patterns of variation and a tool called multivariate analysis. I love this tool because I think as a chemist, scientist, generally we only want to look at one variable at a time or make one change at a time. This is a tool that allows us to look at multiple variables at the same time. And when we're looking at variation in processes, there's some subgroups that we can look at, some of sources. One is positional, one's cyclical, and one's temporal. And positional sources of variation are within a piece related to geography or geometry. Most often it's in location in a batch process. In other words, we have a lot of variation in the same batch, depending on where in the batch it is. And I think for a PTA, it could be, over the course of a run through a molding machine, with the same ingredients, the same pellets, the whole pressure and temperature and everything else, where we have variation in the batch. That would be positional variation. And then cyclical variation is obviously consecutive batches. So if I run the batch again, I get more variation from the first batch, or groups of pieces or consecutive pieces. And then temporal variation is over time, where shift to shift, I get variation, day to day, week to week. All right. The tool, multivariate, it's called a multivariate chart. And the way I like to explain this one is, my wife, as you guys, some of you may know, um, she had a frozen yogurt shop that she owned and ran for 8 years, sold it a couple of years ago. But let's say she lost her mind and decided she wanted to get another second one, right? Or third one. Um, there's an opportunity here, where you can look at a whole bunch of different variables at the same time and get a graphical representation to help with decision making. So in this case, you can see store location, what town is it in, what city is it in, is is it near a mall, is it near school? Talking about frozen yogurt. And again, we kind of want to look at all these things, how it relates to profitability. So store location might be one variable that we're looking at. Two, store size. Is it 1,000 square feet or 4,000 square feet? What does that look like? Um, so store size, store location, and I can look at the whole bunch of and profit all at the same time on the same plot. I have a pretty good video that I like that explains multivariate analysis pretty simply for those of you that are more interested in this tool. But that's what multivariate analysis is. But it allows us to make decisions using multiple variables. And so let's look quickly at classes of distribution. This is important, as we start to get into hypothesis testing, and also when we get into control charts and understanding if I have a given set of data, what distribution am I going to use? Do I have in front of me when I plot it? And based on that, what tools do I use to analyze the data? Binomial distribution. Now we're talking about discrete data. Both of these are both discrete data. And does anybody remember what discrete data is compared to continuous data? These are things that we count, right? So discrete means it's things we count. Continuous means it's things that we can measure. So binomial distribution, it's to model discrete data. It applies when the population is large and the sample size is small. For example, flipping a coin 3 times. What's the likelihood of getting heads 2 times? Or rolling dice. And and being able to predict that way. So I collect a whole bunch of data, whether it's heads or tails, heads or tails, heads or tails. And then again, I can predict, what better degree of certainty what the next flip's going to be. Poisson distribution, very similar, but it's used as a distribution for defect counts and can be used as an approximation to binomial. It's a way to see how unusual event frequency is for a given time period. And I think the example I like to use is LeBron James is averaging 35 points per game. What's the likelihood he will score 12 points in the first quarter of his next game? So that kind of a distribution will allow us to predict something like that. Normal distribution we're very familiar with. Total area under the curves, 100%, shaped like a bell. The mean, median, and the mode are the same as you saw with my weight distribution. And all processes will exhibit a normal curve shape if only pure random variation exists or common causes of variation. Right? If I have special causes of variation, then it's not going to, if I have too many of those, like my trip to work is 25 minutes, and if I start to measure that, and it becomes 26, 28, 31, 29, I'm going to be able to draw a bell-shaped curve like you guys did with my weight. But then if I have constantly having my tires blown, or I'm on a route where there's traffic or accidents or whatever, the process will exhibit a normal curve if only pure random variation exists. All right. And then a student T we'll talk about more as we go on too, but this is a way where I have a small sample size and I can kind of almost do the same thing, make the same kind of predictions, use the same kind of tools, as I can with a normal distribution. This thing, when it came out, it was like splitting an atom, the student T, because it allows us, again, to make a lot of predictions on data with a much smaller. And again, an example would be the polar bear thing, or let's weigh we're gonna weigh what's the average weight of a polar bear. Well, I'm not going to go out and do, weigh 500 polar bears to get a good answer. I might have to get 10 or 12, but the student T, what it does is it numbs down the outliers. A very useful tool. I mean, there's a lot of my students have used this in the final exam, like the final project that we have, which is no big deal, no big shakes. I think you'll enjoy it, but just keep that in the back of your mind, student T. And then the F distribution, used extensively to test for the equality of variances from two normal populations. So I have two different populations and I'm trying to compare those, like testing a new drug for heart disease. You want to determine the significant effects of different dosages. So being the great statistician that you are, you set up trials of 0 milligrams, 50 milligrams, 100 milligrams in 3 groups of 30 people each. Okay, so that's when we use an F distribution, problems like that. So I think, again, the key is based on what I'm trying to understand, which distribution will I use, what formula will I use, and what table will I use in order to do the same thing that I just showed you with the weather, which is just, hypothesis testing like we did. And the chi-square it doesn't mirror real life. It's used for multiple hypothesis tests, like testing the equality between the variance of a normally distributed population and a specific value. Test the quality of proportions, things like that. An example, let's see. Estimate how closely an observed distribution matches an expected distribution, for example. And we don't cover these as much. Most of our work is going to be on this one, on these two. But for Michael and other more marketing, sales, I've had accountants in this class, we will cover binomial and Poisson. All right, so now we can fly through this because we covered it already in the math practice, the inferential statistics and understanding inference. So it's the process of making inferences regarding an unobservable population based on a sample. And so we rely on sample data to draw conclusions about the population from which the sample's drawn. So think about what you guys do already, right? In terms of you don't go out and sample. I guess that's called 100% inspection, I guess. But you don't obviously test in quality control or quality assurance every single sample, every single part that comes through, right? Generally, we have a sampling strategy and we want to be able to draw conclusions about the population just based on the sample. And it's widely used since it's impossible to collect the entire population, or it's too expensive, or it's just too costly. And it contains 2 elements: the inference and then the measure of validity. And the steps involved is exactly what we just did. Find the objective. Is it a 1 or a 2-tail test? Formulate a null and alternative. Select the test distribution and a critical value. Calculate the test statistic from the sample, and then compare that to the critical value, which was taken from a table, and determine if the null hypothesis is to be rejected or not. All right, that makes sense. I think we just covered it, so hopefully it makes a little more sense than if I just showed you this slide. The outcome or conclusion of statistical inference is a statistical proposition about the population. And some of those may be estimating a population parameter. I think predicting is the interest here, is what we're really most interested in. Identifying an interval or region where the true population would fall with some certainty. Deciding whether to reject the hypothesis, making predictions, or clustering or partitioning data in different groups. All right, so that's inferential statistics, which we're going to pick up big time next week with hypothesis testing. And sampling techniques and uses. Population is the entire set of objects of observations in which one is interested in drawing conclusions about or making generalizations based on representative sample data. And we can't do that, so we have to sample. And the process of selecting a subset of observations within a population is sampling. It's used extensively to collect information. Think about it, guys. We use samples of my weight, right? It wasn't like I was taking weighing myself every second for the last 770 weeks. We're using a sample and trying to make inferences about health or lack of thereof. The advantages, it's usually impractical and impossible to collect data for the entire population, cost, too much time, etc. The advantages are lower cost, faster data collection, easier to manipulate. And uses of samples, estimating population parameters, and hypothesis testing, testing a statement about the population characteristics using sample data. Basic sampling strategies. Here's 6 of them. Go through them real quick. Simple random, match random, stratified, systematic, proportional, and cluster. So match simple random in a way that each item in the population has an equal chance of being selected. There's no bias involved in the sample selection. It minimizes the variation between the characteristics of samples in the population. It's the basic sampling strategy. Match random are samples randomly selected in pairs, each of which has the same attribute. For example, researchers are interested in understanding the weight of twins, the difference between a set of twins of weight, understanding the patient's blood pressure before and after taking some medicine, things like that. That's matched random sampling. Stratified is population can be grouped or stratified into distinct and independent categories. And each category can be considered a subpopulation. Stratified samples are randomly selected in each category. For example, a fruit store wants to measure the quality of all their oranges. They decide to use stratified sampling by region to collect sample data. Since 40% of their oranges are from California, then I take 40% of the sample, and I might sample other areas too, Florida, whatever, is selected from the California oranges subpopulation. And systematic sampling, regular intervals based on an ordered list where items in the population are arranged according to a certain criteria. For example, we're sampling every 5th unit produced on the production line. All right. And cluster sampling is a sampling method in which samples are only selected from certain clusters or groups of the population. Selecting samples from the region where researchers are located so that the cost and time spent on traveling is reduced, for example. That's sampling. Again, none of this is on the exam. I keep saying that, so you're saying, what the hell's on the exam? Don't worry, we'll have a huge review at the end, so you'll guarantee you get 100. Sample size, again, statisticians love to turn this into a science even. Sample size is a critical element that can influence the results of being able to make inferences about our population. The smaller the sample size, the higher the risk that the sample statistic will not reflect the true population. And I think the student T distribution helps with this. But the greater the sample size, the more time and money we will spend on collecting the samples. So there's a balance. So there is a formula for continuous data and discrete data on what's the sample size that I need. And there it is. The equation for the sample size of continuous data. So the number of samples is going to be equal to the z-score, or how much a given value differs from the standard deviation. We did that. Remember the z-score? We did that when we were doing my weight. The estimated standard deviation of the population divided by the desired margin of error. And that will tell us, we're using, especially when we're doing capability analysis, which we kind of covered a little bit. We're going to cover more of it. We want to have at least 30 samples. But there's a number that is statistically correct in terms of the number of samples if the calculated sample size is over 5% of the population, then you can discount using the following equation. I don't want to sample 5% usually. And then discrete data, which is stuff we count, polls, coin tosses, dice, poker machines, things like that. The equation for the sample size is here. Z-score, proportion of one type of effect, proportion of, we're going to get into a lot of that when we get into, it's almost one of the last hypothesis tests we do, and we actually do a poker machine to find out if the poker machine's broken or not. And again, if the calculated sample size exceeds 5%, discount using this formula. Not on the exam, just for your exposure. And the main thing today is, like, I wanted to get into, is I'd like you to take away is just the steps that we take for hypothesis testing. And sampling errors, there's random sampling error due to observations being selected randomly. It's inherent in the sampling process and beyond your control. And then selection bias, where there's non-random variation due to inadequate design of the sampling. It can be improved by adjusting the sampling size and sampling strategy. For example, if I want to know the quality of my part, but I only sample for a shift, for example, that might be a selection bias. And that is where we're going to stop, because next week we're going to jump into the world, or 2 weeks, we're going to jump into the world of hypothesis testing. You guys okay with waiting 2 weeks? Because if not, I can probably record. But I think it's, I think hypothesis testing is something that it might be nice for you guys to ask questions as we go through it, versus just watching a video. I don't know. You guys okay with waiting 2 weeks? Because
yeah, that's fine.
Trip to Illinois. All right.
Yeah, that works.
All right. Thank you, people. No homework. Everybody showed up too. I'm so happy. Have a great week, people.
All right, have a good one, Bill. Have a good
Awesome.
trip.
Thank you, Bill.
I'll send you a recording.